This. So, and yeah, dear students, schön Sie jetzt online zu sehen. Heute Vormittag hatten wir ja Vorlesungen sowohl für Master als auch für Bachelor. Das ist mir natürlich eine große Ehre, Ihnen also Carl Engelbrecht vorzustellen. Wir haben gerade schon festgestellt, dass wir uns sehr wahrscheinlich schon 1988 getroffen haben, aber wir haben uns beide nicht mehr daran erinnert. Aber wir waren am gleichen Ort. Also lassen Sie mich kurz zusammenfassen. Karl Engelbrecht ist ein sehr erfahrener Luft- und Raumfahrtingenieur mit umfassender Führungserfahrung sowohl in Linien als auch im Technikmanagement sowie in der Leitung interner und externer Teams. Aktuell ist Karl Engelbrecht Acting Program Area Manager für Mond- und Planetenmissionen im Civil Space Mission Area der JHU-APL, und das steht für Johns Hopkins University Applied Physics Laboratory. Und er ist stellvertretender Programmmanager für das Applied Physics Laboratory Anteil an der Europa Clipper Mission der NASA. Er hat langjährige Projektleitung, unter anderem in Europa Clipper, New Horizon, das MISE-Instrument, die Upper Stage der Solar Probe Plus Mission sowie verschiedene elektrische und chemische Antriebssysteme. Leitungserfahrung in mehreren technischen Gruppen bei APL, also die Applied Physics Laboratory, und auch bei General Dynamics. Sehr breite technische Expertise in Analyse, Design, Beschaffung, Integration und Test von Raumfahrtantrieben für Missionen von Erdorbit bis Deep Space. Unter anderem haben wir gerade schon gesagt, die NASA Galileo-Mission, ne, Magellan, Cassini-Mission, Messenger, Deep Space One, New Horizon und Ariane 5. Fundierte Erfahrung in Test- und Startanlagen in den USA und Europa sowie gute Kenntnisse auch der deutschen Sprache. Berufliche Stationen sind eben neben der JHU APL General Dynamics, das Jet Propulsion Laboratory sowie eine Tätigkeit als Entwicklungsingenieur bei Astrium, damals in Bremen, heute Airbus oder Ariane Group in Bremen. Und zwar an dem Rollkontrollsystem. Ich habe Ihnen das ja vorgestellt, bei Ariane 5 haben wir ein ähm, monergoles Rollkontrollsystem mit Clustern von jeweils 3 bis 4 400 Newton Triebwerken. Ne? Pitch and Yaw Control. Ne? So ausgezeichnet mit zahlreichen Preisen von NASA, APL, JPL und General Dynamics für technische Exzellenz, Führung und Beitrag zu Raumfahrtmissionen, Senior-Member der AIAA und früherer Vorsitzender der AIAA Liquid Propulsion Technology Komitee. Ja, und wie ist das jetzt zustande gekommen? Ich war im Rahmen einer Reise des Ministeriums für Wirtschaft seinerzeit noch im Frühjahr in den USA und habe dann an der Johns Hopkins Universität Karl Engelbrecht auch kennengelernt. Er hat dann auch uns da gut ausgetauscht zu dem Thema eben Propulsion. Und er ist im Prinzip einer der 150-prozentigen Propulsion-Ingenieure, die Sie sich eigentlich nur vorstellen können. Weil gerade das Thema Propulsion bei diesen Missionen ist sicherlich neben der Missionsarchitektur, also wie kommt man zu dem Planeten, eines der wichtigsten Aufgaben, um überhaupt diese Mission zu erfüllen. Und ich freue mich, dass er sich bereit erklärt hat, uns hier einen Vortrag zu geben. Ich habe ihn gefragt, ob er ihn in Deutsch oder in Englisch macht. Er präferiert eben in Englisch, das ist ja für Sie alle kein Problem. Ja, und so würde ich jetzt gerne ähm, das Wort übergeben an Karl Engelbrecht.
Thank you very much, Mr. Ellerbock, Hartwig. What you've said is I have become an old man. And thank you for the kind words. I'm sure I don't live up to all of them, but I appreciate them. I'm sorry I'm speaking in English. I used to speak German better, but ich bin aus der Übung geworden. So I will speak in English. Now, let me test if I change the page. Does it go? So Mr. Ellerbock asked me to talk about my favorite subjects. Carl Engelbrecht and propulsion. So I'm happy to talk anytime about these subjects. I hope I don't bore you too much. Let's see if we can change the page. So my education was in an in-tube ramjet. We ran a projectile down this filled with combustible gas, and we were able to accelerate it. And this led me to become a propulsion engineer. And I went off, as Mr. Ellerbrook said, to the Jet Propulsion Laboratory, and I worked on the Magellan. We in English, Magellan. However, he said his name in Portuguese. So this mission was launched on the Space Shuttle Atlantis, and it was the reason we know so much about the surface of Venus. The propulsion system was a simple blowdown monopropellant system, but we had a large solid rocket motor to put us into orbit. I'm going to make this a little smaller. So I'm sad to say that most of these thruster types that we used back in the 1980s are still available in production. We're seeing recently some new technologies coming out in propulsion, but a lot of what was good then is good now. So we had two big solid rocket motors for this mission, a big solid rocket motor on the inertial upper stage. This is the space shuttle. You young people may not remember that, but that used to be what we launched most things on. And it had a solid rocket motor on it. And then we went off, and then there was a Star 48B, which was made by what's now Northrop Grumman in Elkton, Maryland. And this had never been flown before, not spinning. So we put on several of these hydrazine monopropellant thrusters, 400 newtons, just for attitude control, pitch and yaw attitude control of the solid rocket motor. And then after we got into orbit, we never used these large engines again. We also had 22 Newton and 1 Newton thrusters for attitude control in orbit. With the big solar arrays, even though they're small because we went close to the sun, Venus, we didn't want to be spinning. So we added this propulsion system. It turned out they worked. The solid rocket motor was quite good, and we used almost no propellant for attitude control getting into orbit. And this was exciting for us because we had more propellant to last longer in orbit. Let me say that if you have questions, I don't mind taking them. I know that there'll be question and answer at the end. But it's difficult for me sitting here talking and looking at my screen. I don't know if what I'm saying is getting lost or boring or whatever. So if you have comments or whatever, feel free to ask. The next project, Galileo, I had a great opportunity to work with the MBB at that time, Messer Schmidt Bölkow Blohm in Ottobrunn. They built the propulsion module for Galileo, and I was at the JPL, so I was part of the customer. Here I am working with the spacecraft. So I'm nearly 2 meters tall, so my whole career, one of my challenges has been bunny suits. I was very proud of this picture. And then I got called into my boss's office and was written up for a clean room violation because my trousers stuck out of the bottom of the bunny suit. What can you do? So as Mr. Ellerbrook said, this spacecraft was supposed to launch in 1986, but the Challenger space shuttle blew up, and so we had to change. We clearly couldn't launch since that was our launch vehicle, and then we had to change the spacecraft. Originally, we had an upper stage, which was the cryogenic liquid hydrogen, liquid oxygen stage, Centaur upper stage. But then the safety people didn't want liquid propellants of that magnitude in the bay. So we went to inertial upper stage, same as Magellan. But this didn't have the energy, so we couldn't go straight to Jupiter. So now we had to go to Venus and have a tour. I'll show you that in a second. But that resulted in this bus shade here to keep the spacecraft cool. The spacecraft was, of course, designed to stay warm because we went to Jupiter. So we had to add this, and we had to add a tip shade for the antenna, deployable antenna. And we'll talk about that in a minute. This spacecraft is nuclear powered with radioisotope thermal electric generators. And here you can see the MBB 10 Newton thrusters. Because of our convoluted path, we got to do some additional things. We got to have we got to see an asteroid, which allowed us to find an asteroid moon. And then ultimately, we dropped the probe into the Jovian atmosphere. So here's our convoluted path. We had to go by Venus, and then we flew by Earth. This, of course, meant since we had plutonium dioxide on board for our radioisotope thermoelectric generators, also our radioisotope heater units, this created lots of trouble for making sure that we had a very, 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 very low likelihood of impacting on our flyby. And so we had a lot of excitement and analysis, but it ultimately took us 7 years, 1989 to 1995, 6 years, 7 years, to finally get to Jupiter. Here's Jupiter's moon, a Galileo picture of Jupiter's moon. I'm going to be talking about that later. So here is the retropropulsion module. You can see here is the spacecraft showing, sadly, that the high gain antenna never fully deployed. It was designed to deploy early, and because we had to wait a few years to fly by Venus and it got hot, when we finally tried to deploy the antenna, it never did. And this meant that we had significantly less science from the Galileo spacecraft than we could have had because we had to send everything down on the low gain antenna. Here you can see the radioisotope thermoelectric generators. And at the bottom here, we have a probe, the Jupiter atmospheric probe. And here you can see the main engine, the 400 Newton engine. I made a mistake here. This is not ANO, this is MBB Autopun. And the main engine could not fire until the probe was released. So it sat there very calmly for 6, 7 years before it finally got to be able to be used. This spacecraft was a spinner. So you can see the tanks have outlets on the side as well as on the top and on the bottom. This 10 Newton thruster caused a little bit of trouble. It was the same thruster for the TVSat spacecraft and Galileo. We qualified it for Galileo. It sat on the launch vehicle, ready to launch, and then Challenger blew up and it came home. In the meantime, TVSat flew, and it turned out these engines were thermally unstable. So you can see that they have fuel regenerative cooling here. The tube goes around the thrust chamber. And because we're flying for so long, we had to consider gas that had dissolved into the propellant, so fully saturated gas. And after the pressure dropped through the lines, there was gas here. And so the thrusters for certain duty cycles, certain steady state durations of firing were getting too hot. And the TVSat, we found this out because the TVSat spacecraft fired its engines and they failed in flight. The good news is TVSat was already finished with its mission. It had another problem. And the other good news was we found this out. So on Galileo, we only used these thrusters in pulse mode. You can imagine millions of pulses. Because this part of the spacecraft spun, it's spin stabilized, the bottom part spun, but the part with the instruments didn't spin. This was an interesting part of the spacecraft, but the retropropulsion module spun. So it was already a lot in pulse anyway to make sure that they were in the right spot when they fired. But lots of interesting propulsion going on with this spacecraft. We learned a lot also about in long duration flight, the dinitrogen tetroxide oxidizer. leaches iron from stainless steel, and then this comes out of solution when you saturate, and that can block filters, clog filters. We call this flow decay. So late on this mission as well, we changed from stainless steel plumbing in the oxidizer system to titanium, which helped with that problem a lot. Here's the 400 Newton bipropellant thruster, which I understand is still being used a lot. The 10 Newton thruster is still being used, but they've changed it, I think, to a platinum rhodium chamber, or at least a platinum chamber, and they don't need the regenerative cooling anymore, and it works great. This gentleman, I believe, sadly has passed away, but it won't keep me from saying if you stick your head behind a rocket motor, this is what happens to your hair. Sorry if that offends anyone, but that's my hairstyle as well.
So, Sie sehen, warum sitze ich jetzt in der Vorlesung mit einer Glatze? Man hat die Erklärung gegeben dafür.
There's a famous king, Karl der Kahle, in the history of Germany.
That's
But
right.
everyone told me, yeah, you're not Karl, you have a Glatze. But anyway, I like to be Karl der Kahle. Anyway, Cassini Saturn Orbiter was the next spacecraft I worked on. I was responsible for the main engines. The spacecraft, you can see, JPL learned our lesson, and we did not have a deployable a high gain antenna. Instead, we had a regular high gain antenna, which was very much like the one on Voyager, which JPL built and is still operating. And from a propulsion point of view, if you look at the Voyager propulsion system, 1977 launch, many of the thrusters, the 1 Newton thrusters, are still in production and still used from what's now L3 Harris Rocket Research in Redmond, Washington, MR-103Cs. This spacecraft is also a radioisotope thermoelectric generator. We're photoshopped in. We would never be standing so close, although that, again, might explain my hairstyle. This had on it a probe that went into the atmosphere of the moon Titan, named after the Dutch scientist Huygens. We were not behind that, so we could use the main engines all the way, but this spacecraft also had a convoluted flight to Saturn. But here's a proof of the value of the science of the spacecraft that we build. This is what we can see that Titan looks like now as opposed to before. It's the same like Venus before and after Magellan is quite exciting. The spacecraft propulsion system for Cassini built was huge. The fuel tank on the top, the oxidizer tank on the bottom for the main engines. In those days, we didn't have good qualified dual mode engines. So you're a propulsion class, so I assume you know that dual mode means nitrogen tetroxide oxidizer and hydrazine fuel. So here we have MMH and hydrazine. The advantage to this propulsion system is the tanks are about the same size. The mixture ratio is about the same as the ratio of the densities of the propellants. So in order to do small attitude control, we needed a separate hydrazine system, which we had. Here's the pressure tank for the bipropellant system. This is a blowdown system, but we also have a recharge tank, high pressure helium stored in a small tank, and that allows us to recharge the hydrazine tank. And so this worked very well, a whole bunch of small monoprop thrusters. The two biprop engines, this is the Marquardt R4D11, heritage to Apollo, very robust engine. Unfortunately, that means a relatively low ISP of about 311 seconds, 311, but very high heritage, great for these long missions. The pressures in the tanks are affected by temperature, and the mixture ratio changes because of that. And so this engine's very robust to that. But we also needed to have redundancy. On Galileo, we did not have main engine redundancy. This caused a lot of anxiety. So on Cassini, we had two, which meant we had to have flex lines and gimbals so that we could point whichever engine we were using through the center of mass. This added a lot of complexity. We had to test at the main engine assembly level. And because of the flex lines, we ended up with some chugging. Chugging is a low frequency instability. That's coupling between what's going on in the chamber and in the flexible feed system. So we spent a lot of time dealing with that. And here you can see the flight engines in the back of the spacecraft. The other thing is Cassini flew through the asteroid belts. And so we were worried about, also, we flew through several times through the rings of Saturn. We were worried about damaging these thrusters. They are columbium, or it's a version of niobium with disilicide coating. This disilicide coating protects the niobium or the columbium from oxidation. The niobium is very strong at high temperature, but it's not oxidizer resistant, so we have this coating. Unfortunately, the coating is like glass, so it's brittle. So if you take a micrometeoroid impact or ice particle from the rings of Saturn, that would cause this to spall, and therefore the engine would fail. So we have this main engine assembly micrometeoroid shield that we had to open and close. You can see here it's open, and then it folded up over here. All these things you have to do when you go to other planets and spend billions of dollars.
Okay, maybe Carl, one comment to this slide before. The R4D engine, for your information, is also the engine which is in use for all the ATV missions
That's correct.
and also currently for the ESM version. Yeah.
There are two new versions of the R4D, the R4D 15, which is called a HIPAT, which is rhenium, a rhenium chamber with an iridium coating. And so you can get like 330 seconds, so a 20-second ISP improvement. And there's a dual mode version, which uses hydrazine as the fuel, and you get a few extra seconds for that as well. And again, this goes all the way back to the command service module. Carl Steckman, who designed this engine, happily is still alive in his 90s. And
Yeah, he's a nice guy, yeah.
so here, Hartwig is that thruster we were talking about earlier. This is the 400 Newton engine, which now has a new life. It used to have a life for attitude control of the Ariane 5 launch vehicle, and now it's got a life for deorbiting. I went to Germany for a while after working on Galileo. I met some people and they offered me a job, and I was very happy to go. And I worked on this system. This is a blowdown monopropellant system. In other words, no pressurization system. When I worked, there were 4 tanks, then they expanded to 6. And these thrusters are here. Worked very well. Here you can see a port to allow pressure testing. So this is not a flight engine, but and a big catalyst bed, so lots of capillary tubes to spread the hydrazine. This thruster worked very well. One of the interesting things about this system was there was a lot of water hammer because such a large thrust meant large flow rates of hydrazine, and when you open isolation valves, you get large surges. And these surges in hydrazine can result in adiabatic decomposition. In other words, the gas that's trapped in the propellant gets compressed and gets hot. And this heat then causes the nearby hydrazine to decompose, which causes more hydrazine to decompose, and you end up with premature unplanned disassembly. So on this system, we put an orifice that bypassed the isolation valve so that there was never a pressure drop across the isolation valves. You could never do this with a spacecraft propulsion system, because if the downstream engine leaked, then you would leak all your propellant. But because this system was just used for short periods of time, we could take that risk, very small leak rates. The safety people bought it, And this simplified our propulsion system significantly. We didn't need to have orifices or cavitating venturis to prevent adiabatic decomposition, and we could have high performance with relatively low tanks. This was a very successful system and a great honor for me to work and learn there. After I came back to the United States, I worked on the Deep Space One mission, but in this case, I worked as a feed system lead for the NASA's Solar Electric Propulsion Technology Application Readiness System. Deep Space One was a part of several deep space missions, New Millennium missions that NASA went forward to try and develop technology. So there's very limited science. The spacecrafts were inexpensive, but we could demonstrate different technologies. And one of the main ones on Deep Space One was solar electric propulsion. It worked great. We flew by some asteroids and comets, but like I said, it wasn't a lot of science, but it's a complete different world for me. This is ion thruster, so millinewtons of thrust, but thousands of seconds of ISP and a xenon propellant. We also had a hydrazine attitude control system, but that was not so exciting. Here's a picture of the ion thruster firing. It's gimbaled. And here's a drawing of the spacecraft, huge solar arrays because of the kilowatts required for the ion thrusters. Turns out the xenon feed system is very different from a hydrazine or a biprop feed system for obvious reasons. The main one is the cathode flow rates for the ion thruster are about like leaks in a chemical system. So it was a learning experience for me. Then my wife and I had a child, and it became too expensive to live in Los Angeles without driving an hour. So I moved up to Seattle, where I went to university, and I started working on the company that was then Primex Aerospace, Primex Technologies, but originally Rocket Research, now part of L3 Harris. While I worked there, I had a colleague who had worked there her entire career, and she had 15 different business cards because the company kept getting bought and sold and changed its names. But anyway, it was Primex at the time where we built the upper stage, the orbit adjust maneuver for the Athena launch vehicle. This was a blowdown monoprop system. Interesting to me because similar to SCA, the attitude control system on Ariane 5, you have only very high thrust. So it makes the feed system simpler. You have gravity, and you don't have to worry about long-term things like temperature changes in tanks. But it was still exciting. And while working there, I also worked on hydrazine systems and some biprop systems. We built the hydrazine system. You can see the propellant tank here for the European Smart 1 mission. I did not have anything to do with the electric propulsion there, but here I am, and this is the hydrazine system which we delivered to Linköping for the Swedish Space Corporation. Then I worked Mercury Messenger. You're going to hear more propulsion now instead of just stories of Carl's life. This is the first spacecraft to orbit Mercury, and getting to Mercury is very difficult, as our European colleagues in working Bepi Colombo know very well. Getting to Mercury, you have to slow down a lot to get down there, and then you want to not fly by it. So very challenging propulsion-wise. Here you can see the pressure and tank. We had a big biprop system on Messenger. We had to get in orbit. This is a picture of the spacecraft with the main engine firing. The trajectory, so this was a low-cost mission, unlike Galileo and Cassini, which were what's called flagship, very multi-billion dollars. This was much less. So we had to get from the Earth to orbit around Mercury, and this took many years, 7 years. And we had an Earth flyby, 2 Venus flybys, and 3 Mercury flybys. So the propulsion system had to operate, the biprop system had to operate over and over and over again, years and years in between. It's very difficult to maintain the pressures. So it's easy to increase the pressure using a regulator, but it's difficult to decrease. And as you get closer to the sun, as you may expect, you get warmer. And as you get warmer, your pressures increase, and therefore your mixture ratios resulting from different oxidizer and fuel um, pressures change. So you better have a very robust propulsion system, very robust main engine. The other thing is, if you're going to use all that propellant and you don't have much money, your spacecraft is going to be sized by your propulsion system. So this is a dual mode system, hydrazine and dinitrogen tetroxide, NTO. This propulsion combination typically has a volume ratio of 2 fuel to 1 oxidizer. So we have here a fuel tank in the middle, an oxidizer tank, and in the front another fuel tank. You can see that the one tank is close to the sunshade, the other is farther apart. This causes thermal concerns. Here we have a main engine. This was a Lyros engine, very robust. Again, relatively low performance. If you want high robustness, typically you don't drive a Ferrari. If you want high performance, you drive a Ferrari, but you have to do maintenance regularly. So this is a low, this would be an Opel maybe. We launched upside down like this. Here's the launch vehicle adapter, which means the tanks are upside down, the outlets are up. So the PMDs, the propellant management devices for these tanks would have been very complex. So we ended up going with no PMDs in the tanks. And instead, we have a diaphragm tank here, an auxiliary fuel tank, which had a diaphragm. And then before every maneuver, we would use propellant from this tank, fire thrusters that faced aft. This would drop the propellant in the tanks to their outlets. And then we could do the main maneuvers. This is the pressure in tank, helium tank. So this system had a huge propulsion system relative to the spacecraft size. We had to have thrusters pointing in all directions because while we were close to the sun, we had to keep the spacecraft behind the sunshade. This created lots of propulsion challenges. It was an exciting mission to work on. It was very successful. It has now made a new crater on the surface of Mercury. We ran out of propellant 7 years after the end of the nominal mission. Very exciting thing we did because we had no diaphragms in the main fuel tanks. Once we ran out of propellant, we used the helium through the hydrazine monopropellant thrusters to give us another several weeks of operations, some little bit more delta V. As far as I know, it's the first time anyone has used a catalytic monoprop thruster as a coal gas thruster, and it was exciting. And the system engineer got an award for that. He didn't share it with he didn't share the money with the propulsion engineer, but that's okay. So quite the opposite. Here's the New Horizons spacecraft. And this went to Pluto and the Kuiper Belt. Here's Pluto and Charon. The picture is taken from the spacecraft. Obviously not solar, but this is just a thermal and a mechanical simulation of the radioisotope thermoelectric generator. But this spacecraft, because we didn't orbit, has a tiny propulsion system, 80 liters of hydrazine. And all we have, you can see here, are little tiny thrusters. These are 4 Newton and these are 1 Newton thrusters for attitude control and also small trajectory corrections. You can see as I get older, the bunny suit problem persists. Though now it's long enough, it makes me look like the Michelin tire man, I think. But anyway, New Horizons was a fascinating mission. Very, very tiny spacecraft, as you can see, about the size of a grand piano, on top of the biggest launch vehicle we had at the time, and it went all the way to Jupiter in about a year. It at that time was the fastest thing ever launched. And it studied Pluto. In the meantime, between launch and arrival, Pluto got downgraded from a planet to a dwarf planet. Shortly after Pluto, we had science and a gravity assist at Jupiter. We got to Pluto many years later, 9 years after launch. And shortly after that, we did a redirect using our propulsion system to see this Arakot, this primary contract binary object in the Kuiper belt. To me, it looks like a snowman with nose and a mouth and eyes. They hadn't even discovered this when we launched, and then we changed trajectory and we flew by that a few years later. 2014, it was discovered, and we flew by that. I can't remember now, 2018, 2019, something like that. Probably says it here, 2019. So fascinating mission. Propulsion-wise, not so interesting. Blow-down monoprop. Now we're back to talking about Carl. I worked also on stereo. In the meantime, by the way, I didn't mention all of this is at the Applied Physics Laboratory. This is rocket research. This is the Applied Physics Laboratory. We moved to the Washington, D.C. area where I work now. This is all the Applied Physics Laboratory. This propulsion system was built in my previous employer, but we were now the customer, and you can see two hydrazine tanks. It's a monoprop blowdown system, two spacecraft flying in heliocentric orbit, studying the sun in stereo. It's clever. This is a Solar Terrestrial Relations Observatory is the acronym, but we were also, because we had two spacecraft, we could get 3D images of these coronal mass ejections. Again, not a very interesting propulsion system, blowdown monoprop system, hydrazine. And then two other spacecraft in the meantime, as Mr. Ellerbrook told you earlier. I became a manager. I didn't do so much propulsion, but I still helped and did work with the other spacecraft, the now Van Allen probes. The RBSP is a radiation belt storm probe. Two spacecraft, as you can see, going in low Earth orbit through the radiation belts and studying. Learned a lot about that. I was involved in propellant loading. Here's the usual propellant loading, and also propellant loading for the solar probe mission. The solar probe mission is a fascinating mission. Because we get so close to the sun, it's again difficult to be solar electric, and but it was getting more and more expensive and difficult to get radioisotope thermoelectric generators. So we proposed this mission as solar. The solar arrays, when we're far from the sun, the solar arrays are out like this. And as we get nearer the sun, they get smaller and smaller so they don't get too hot. And when we're right near the sun, most of the solar array sits behind this thermal protection system. And just a little tiny bit of the solar array is out. We obviously don't need much surface area, and we're pumping water like crazy through that to keep it cool. And that water then gets pumped through these radiators here and cools it. And so we keep it from burning up. All of the instruments are in the back, hidden behind a thermal protection system. This spacecraft continues to fly very successfully. So far at the closest approach, 120, I'll say in kilometers per second, 200 kilometers per second. It's the fastest man-made thing ever. But still 0.1% of the speed of light or something, very compared to the speed of light, very, very slow, but still very, very fast compared to what we normally build. This spacecraft you can see is also a very small spacecraft so that we could get it going so fast. And then I came back into propulsion because we had a new mission, Europa Clipper, and here's the Moon Europa. If any of you read the book 2001, A Space Odyssey by Arthur C. Clarke, at the end of that book, the people, the creatures who created the monolith, send the people of Earth a letter saying, you can go and study anything you want, but stay away from Europa. Because even at that time, we knew that there was possibility for life on Europa's, more water on that than on Earth, a big liquid ocean, tidal flexing caused by flying in orbit around such a huge gravitational field. So the moon gets pulled and relaxed, pulled and relaxed. This creates energy, which keeps the water liquid. So very interesting to study. And the monolith creatures told the Earth people to stay away from it because they didn't want us to mess with that. So we're going, but so far the spacecraft is doing very well, and nobody has zapped it out of the sky. So hopefully, fiction remains fiction. Europa has other problems from the point of view of propulsion. We could not orbit Europa because Europa is right in the middle of the radiation belts, and our spacecraft would have gotten cooked too quickly. So we orbit Jupiter and fly by Europa every orbit, which means that we have to do significant propulsive maneuvers every time. And we also have a lot of delta V. We have Mars and Earth flybys on our way there. So far, we've done the Mars flyby. The Earth flyby is coming up. We have a very challenging Jupiter orbit insertion maneuver. And again, as I said, once we're in orbit around Jupiter, we have to do a lot. Plus huge solar arrays, no radioisotope thermoelectric generators as with solar probe, Van Allen, as with solar probes. So we had to use solar arrays. They're huge. They were built, by the way, by Airbus in the Netherlands. They were delivered by Airbus in the Netherlands, but a large portion of the solar arrays themselves were assembled in Airbus in Ottobrunn. Very successful, great colleagues there. So we had thrust requirements for orbit insertions. We had small IBIT requirements because we have large solar arrays. All these things caused us to have a lot of time to spend trying to design this propulsion system. We went to monomethyl hydrazine instead of neat hydrazine. So this would have been nice to have a system like Cassini where we had both monopropellant and bipropellant, but we didn't have enough power. So we gained 10 degrees Celsius by going to monomethyl hydrazine. This has a freezing temperature of minus 56, and then we're limited instead by the oxidizer, which is about minus 15. But you can't have the nice small minimum impulse bits associated with monoprop thrusters. So this cost us a lot of propellant and fighting with the attitude control people. And we had to change the soft goods, the kinds of Teflons we used to be more robust to radiation. So it was, this propulsion system was very different and new. Here's a picture of how big the solar arrays were on Europa Clipper. If you play basketball, as I used to, you have a reference of how big they are. This is the very large high gain antenna as well. And here's a nice picture. Part of the solar array challenge was associated with these ice penetrating radar that we put on the solar array. This solved the instrument people's problems because they have a lot of electromagnetic cleanliness requirements, but it caused a lot of headaches for the people who built the solar arrays. This is the surface of Europa. Here's the propulsion system. So the oxidizer tank is in the lower cylinder and the fuel tank you can see here. And here's all of our plumbing. Down here are the engines. We ended up with 24, 26 Newton bipropellant thrusters built by Moog, platinum rhodium chambers. Very robust because, again, we're flying a long time and the mixture ratios can change. But we cleverly completely separated the fuel and the oxidizer systems. With Galileo, Cassini, we had to deal with oxidizer vapor migration. And the oxidizer vapor goes up and mixes with the fuel at the regulators or downstream of the regulators. And this causes something called FORP, fuel oxidizer reaction product. And it was blamed as the cause of the Mars Mars, I'll remember what that stands for, mission failure. And on Cassini, it required and subsequent missions, lots of ways to isolate the fuel in the oxidizer. We avoided that problem on Messenger and on this system by having separate fuel and oxidizer pressurization systems. On Messenger, this resulted in large mixture ratio excursions that the engine had to deal with. But because we had hydrazine, it worked great because we went to oxidizer depletion, and then we did the rest of the spacecraft maneuvers with the monopropellant. But this system, we couldn't have hydrazine, so we put in here some Venturi flow meters. We put cavitating Venturis in the flow. We measure the pressure drop between the inlet and the throat of the Venturi, and we can use that to measure flow rate. And so we have a bang-bang regulation system, which means not a mechanical regulator, but solenoid valves controlled by downstream pressure transducers, which is the same way we control the pressure on our xenon feed system. So we had a lot of experience with that. And then we can change the fuel pressure and the oxidizer pressure relative to each other as we fly based on how much fuel and oxidizer we are expelling relative to each other. So this allows us to control residuals while having completely separate fuel and oxidizer systems and avoiding the problem of fuel and oxidizer vapor migration and mixing. Fascinating propulsion system built at the NASA Goddard Space Flight Center. I'm very sad to say that this building, with our new government, they are significantly reducing the size of NASA Goddard, and this building will be destroyed. Sad to say. Here's a picture of the back of the spacecraft, and you can see 4 rocket engine modules with each has 4 aft-facing engines and 2 roll thrusters. To get the combination of low I bits and all, we did a trade and we ended up with a lot of small engines instead of 1 or 2 big ones. This also dealt with not having to have micrometeoroid protection because we don't have, none of these are single point failures. It dealt with a lot of issues, a lot of concerns by having all of these engines, but also added complexity, of course. These are platinum rhodium. Anyway, that's what the back of the spacecraft looks like. Completely redundant. We use 8 of these 16 aft-facing engines for Jupiter orbit insertion. Completely redundant set if we need them, but we'll be using them. We are already using them for all of our trajectory corrections on the way to Jupiter, and we'll be using them, all 24 of them. Here's a picture of the Proud Papa. So as I was saying, we want to make sure we don't contaminate the spacecraft. I mean, not the spacecraft, Europa, if we were to accidentally crash into Europa or something. So we have very strict planetary protection protocols. Double masked, you can't see the mask underneath that, double gloved. The good news is we built this spacecraft during the COVID pandemic. And the good news is during the COVID pandemic, you couldn't have been in a safer place with all this masking and everything. So we were able to do the integration and test while a lot of other people were not going to work. Again, you can see the pressurization and the liquid, the fuel and oxidizer systems here. And you can see for the photograph, they took off the red protective covers and you can see the roll thrusters here. And you can see the aft-facing engines here. They have what we called wetsuits, like swimming wetsuits on them, rubber to protect them so that the oxidizer and actually they have a coating that helps radiate the heat. And so we didn't want that to be damaged. So they have rubber things on them. We did remove them all. They're all working fine. So that's my story. I got done a little early, so you can ask questions about whatever you want. This is my current employer, the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. I actually work across the street, but we build a spacecraft up here in this part of our facility. So hopefully everyone isn't sleeping. Let me know if you have some questions.
Yeah, thank you very much, Carl, for give us here some insights into your life and the challenging propulsion systems. So I would like to ask the auditorium, do you have questions about the propulsion system, which were used in several missions? So don't be shy. There could not be bad questions, only bad answers.
So you put the pressure on me, I see.
So wait a minute. Um, I would have a question not directly about the propulsion system, but maybe you can tell us something about what you're currently doing at the John Hopkins University. So what are you creating there?
Okay, thank you. First of all, the Johns Hopkins University and the Applied Physics Laboratory are tenuously connected. So they write my paychecks, which I appreciate, but they currently have a Canadian president, and most of the work that the Applied Physics Lab does is Navy related. So we are quite independent from the university. So I'm not a professor or something like that. Just for clarification. Right now, we are working on a bunch of things, but sadly, I can't share those with you because they are proposals, and we don't want our competition to know what we're doing. But I'm working on still the deputy program manager on the Europa Clipper mission, which, as I said, we should be flying by the Earth soon. We have another mission called IMAP, and in my old age, I'm interstellar mapper or something. I can't remember what IMAP stands for. Anyway, I work on that. We just did a trajectory correction maneuver last night, so we're flying that spacecraft. It's going to Lagrange point, an Earth Moon Lagrange point, and it's basically studying space weather and this sort of thing. So I'm working on that. I was working still working the Uranus orbiter and probe. I'm the project manager for the Uranus orbiter and probe mission. But sadly, that did not get included in the president's budget request. So just writing papers now and closing that up. We have in the future a very, very exciting mission, which you can look up. It's called Dragonfly. And we're going back to Titan. This time we're going to fly a rotorcraft. It's always hard to remember not to call it a spacecraft, but it's basically a drone the size of a Mini Cooper, and we're going to fly around Saturn's moon Titan. It's very exciting, very challenging. It turns out that it's very, 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 very cold there, but the atmospheric density is higher than the atmospheric density of Earth because it's mostly methane. So it's a very challenging mission, very exciting. We should launch that in a few years, but I just do little things on that. The propulsion system is being built by Lockheed Martin. Did that answer your question?
Yes, thank you very much. So you talked about this drone. What kind of propulsion system is going to be used there? Is it also liquid-based propulsion, or do you use, I don't know, regular props or?
We use propellers.
Okay, yeah.
It's a rotorcraft, and there's a high density atmosphere, so the propellers fly it. There is a blow down hydrazine monopropellant system on the spacecraft, and then a big parachute. And then as we near the surface, the drone separates and the propellers start working, and it uses itself to land and also to move around. I spent last week sitting on a design review for the Mars sample return mission, the sample return lander. They are on Mars, not enough atmosphere, and so they use large throttleable monopropellant thrusters, similar to what was developed for Viking and then used for all of the previous Mars landers. And that's exciting as well, but they come down and then they drop the rover using ropes and pulley system, and then they fly away so that they don't land the propulsion system, so they don't blow all the sand away and whatever and destroy the lander. But that's more normal. We do the same thing, except that we use our drone for the final propulsion because basically it's electrically powered, radioisotope thermoelectric generator, MMRTG powered, and we can fly as much as we want as long as we have power because we have an atmosphere.
Okay, thank you.
Further questions from the auditorium? Comments, remarks? So maybe, Carl, I have some questions on it. Regarding the mission to Mercury, when you do this with a chemical propulsion system, what is the delta V you have to perform on this system?
So this was a while ago, and I'm old, but I would say 2.7 kilometers per second is my memory.
Mhm.
Delta V for Mercury orbit insertion is almost 1.
Oh, yeah. Yeah, I compared this a little bit with the Bepi Colombo mission, which European, the ESA is flying it with electric propulsion. Yeah. And I think they are currently struggling a little bit because the orbit is not that stable as it should normally be for the spacecraft. So it means it's a question of thrust. They have some disturbances in it, so they changed a little bit the.
So they have an electric propulsion system, and they have, according to what I read, so I know it's okay to share what I read on the internet, so it must be true. They have some power system. They're not giving enough power to the main engine, so they didn't have enough thrust, so they couldn't get into orbit, and they're having to delay orbit insertion. But the
Right.
propulsion system is working fine. People always say, "Oh, it has a propulsion problem," but I, as a propulsion person, want to blame the power people. The power people may blame the propulsion people. That's normal.
That's normal, yeah. So
Yeah. Okay.
related to the Europa Clipper mission, when you go, I know, just previously there was you made a measurement in the Van Allen belt, and did you perform also here, or did you get indication about solar array degradation when they are standing long time in the Van Allen belt?
Yes. So we got a lot of good science information from these spacecraft, but we also got a lot of good technical data on the impacts of the Van Allen belts, being in the Van Allen belts, and how this impacted things.
And what
These
is
were nice small. You can see the spacecraft here, nice small solar arrays because we're at Earth. These spacecraft ended up they finished their mission now, and we pushed them into a safe orbit.
And do you remember what is more dangerous, from the Van Allen belt, the electronic part or the proton part?
I apologize. I'm a plumber, not an electrician. So sorry, I don't have an answer I'm confident telling when I'm being recorded.
Yeah, because since 2012, when Boeing set up their all-electric propulsion satellite systems, there was an interesting discussion I had with one of these main engineers at Boeing, and they said they had two spacecraft in the Van Allen belt, which ended up due to mission failures, but they were connected with them, and they figured out the degradation is not that much as they expected it at the beginning. And that's the reason why they now can design very easily satellites which has open solar arrays running to the Van Allen belt, because when you have electric propulsion for orbit raising, you cannot use this with batteries. You have to open your solar arrays and you will have the degradation of it. And it's not more than 20%, they said, and that is acceptable for a spacecraft for a 15 years mission to do this then fully with electric propulsion. And after that, then 3 years later, all the other one followed. Yeah, Boeing was the first one, and then came Airbus and Thales, and all of them building spacecraft with full electric propulsion for their geosatellites in order to increase the payload mass. Huh? So, and this is now a huge step in the last 10 years for up to 3,000 kilogram of payload on a satellite with a 25 kilowatt of performance, electric power performance. Huh?
Yeah, and I don't know if you use the word in America, we use the word sandbaggers, people who are always saying things are harder than they need to be, the power people, and we always have this fight, and we call them sandbaggers. And so Van Allen probes showed that they were being overly conservative. We fly, and frequently we find out there's a lot more power coming from the solar rays than they told us there would be. So this is not a surprise to me, Hartwig.
Yeah, so, and it changed completely the world. So now it's again changing because geos are in telecom not anymore so much needed as before. Now it goes back more to LEO.
Or very LEO.
Or very LEO.
The impressive thing for Europa Clipper, I was at the Cape Canaveral lots the last few years, and they now have a launch every week, at least.
Right.
SpaceX.
Yeah. So then another question, which I may not completely understood, is for Europa Clipper, why you separated the pressurization of the oxidizer and fuel tank due to the non-return valves were not working very well, and you have a flow back of MMH to NTO, or?
So by non-return valves, I think we call those check valves. Yes. Mars Observer, MO, I think that's what it was. They had a spacecraft. This was the days of faster, better, cheaper at NASA. And they had a spacecraft that was designed for GEO. And you would use your propulsion system within a few weeks, and then you would isolate your oxidizer and do the rest of the mission. And everything worked fine. Then they sent that spacecraft to Mars, and it was a year in transit. And then when they pressurized the system, the propulsion system failed. They had the RF system off at the time, so they never came up with the absolute cause. But they found out that check valves, non-return valves, are very bad at keeping oxidizer vapor from. Sorry, I'm just getting a phone call. I'll ignore it. They're very bad at keeping oxidizer vapor from migrating, and even latch valves are. And so when you are years with oxidizer vapor in your lines, you end up with mixing. And then we looked at previous spacecraft. We looked at Viking, for example, and we saw that the regulator developed a leak, and we anticipate that that was because of oxidizer vapor and fuel vapor mixing in the regulator, causing FORP, causing a particulate, which caused the regulator leak. On Galileo, we saw an increased pressure drop across the fuel check valve. And this resulted in mixture ratio excursions, and it's in the wrong direction. It's the bad direction because you have a bigger pressure drop on the fuel side. So this makes you ox rich, and ox rich is less, is usually higher temperature, more risky. Then the Japanese had a system, Akatsuka, I think it's called, where they fired their main engine and their fuel check valve pressure drop was huge, and their engine ended up blowing up. Fortunately, it was a hydrazine dual mode system, so they went around the sun again and used their hydrazine thrusters to get into orbit. But again, it was the oxidizer vapor and the fuel vapor mixing. So on Cassini and missions subsequent to that, Mars Global Surveyor missions like this, we use pyro valves, and we periodically isolate the tanks with pyro valves. And then this keeps the oxidizer vapor from mixing. We also periodically flush. But to avoid this problem completely, you separate the oxidizer vapor from the fuel. The oxidizer has about 1 bar vapor pressure at room temperature. And so the vapor just goes upstream, and it, even if you have a valve there, it permeates the seat and then evaporates on the other side. So I hope that answers your question, but that's a big problem when you have to keep your biprop system um, not isolated. You have to use it for years and years. Actually, a story. When I was in Bremen, we had that bypass orifice that I was telling you about. It's of Lee Viscojet, and we were working, and we saw that had filters that were brazed onto it, and we noticed that brazed material was not compatible with propellant. So when I went back to JPL from Germany, I noticed that the regulator on the Mars Observer spacecraft had that Lee orifice in it with that filter.
Mm-hmm.
And so they took that orifice and they stuck it in oxidizer vapor, and it clogged up very quickly. And so we believe that what caused the Mars Observer to fail was that orifice got clogged. Therefore, the pressure downstream couldn't get to the sense port on the regulator, so the regulator never closed and the tanks pressurized and ruptured. There's a big paper about this I can send you if you want. But this, to me, was the good luck that I had been I had been by MBB, because I learned that, came back, and then they took that out of the Cassini regulator. It was in the Cassini regulator as well. So this is why you move around and you learn from other people.
Yeah, that's right. Yeah, thank you very much. We do not have this problem with the regular satellites, because when we are finished with the liquid apogee maneuver, we go down in blow down mode on the propellant tanks, and then that's
Exactly.
it. You know? So yeah, and the I think I remember that I saw and took a picture of your plan in your entrance hall, which will fly on Titan, right?
Yeah, that's the what I was talking about, Dragonfly.
Yeah, right.
You probably also saw a model of it sitting there in
Yeah,
the.
yeah. That was quite interesting, to see. I could imagine it would be very difficult to simulate the conditions with the higher pressure methane atmosphere in a wind tunnel, in order to see how the spacecraft, the aircraft or methane craft will work. Huh?
Yeah, you've found the problem we have. How do we refer to it? The rotorcraft, we call it. But if you got a tour of our facility, you would have seen we built this big chamber um, for simulating the atmosphere there.
Yeah, this remembers me a little bit when we were faced to the problem in the Sänger project to simulate for the ramjet engine the entrance conditions. So at first we started with air and using then kerosene in order to heat it up to get the right temperature, but you do not have the right properties then at the entrance of the engine.
Mm-hmm.
So, and after several investigation, we used a refrigerator, which is using laughing gas, and we could then simulate up to Mach 7 the right entrance conditions in a standard test facility. This was a very, very nice experience. So all this came up when you told that you are trying to make a simulation of flying of this vehicle. Yeah?
Speaking of laughing gas, if I may, very exciting to me, new technology coming out now is nitrous oxide and some self-pressurizing fuel like propane. So the same fuel tank that you would use for your grill, if you have a gas grill, and these two propellants are self-pressurizing. They have a relatively high vapor pressure.
Yes.
And so you can very simply build low temperatures. You can 3D print your tanks. You can 3D print your thrusters. They need a spark. It's not hypergolic. but you can build wonderful, very simple self-pressurizing systems, and they're being offered by several companies now. The downside to these is as you use the propellant and it evaporates to keep the pressure, it gets cold. When you evaporate, you get cold, and so then your vapor pressure reduces and your thrust performance reduces. But for small uses, small propulsion uses, this is very exciting.
Yes, I'm supporting here a startup here in Munich at the Technical University, which is using methane and oxygen in this self-pressurization model. And this works pretty well. They have three different technologies in their vehicle. It's a 500 Newton engine, which they used, and would like to do this similar to that what Tom Müller is doing with an in-orbit vehicle. Yeah, and these three technologies is they have a resonance igniter, which is a very interesting thing. You have a tube which goes in resonance with the oxygen. You bring in the oxygen is heating up so high that when you put in some fuel, it directly ignites. So only have two valves to do in this, no electrical system. So this is a pretty nice thing. The second one is then to use the regenerative part of the chambers in order to bring this in a heat exchanger into the tanks so that you can regulate the pressure of your barbecue tanks. Yeah. And the third technology they are currently investigating is zero boil off by using the liquid part and spray this on the gaseous part of the tank in order to reduce the self vaporization of the system when you have a longer phase of Daumen mode of your propulsion system. Huh? So
Fantastic. Fantastic. I'm glad I'm old because I don't know if I could learn all this new stuff. So I'm glad for the young people that will take care of all of this after I'm retired.
yes, and this is why I'm telling this also to all these students, yeah, to motivate them. You can do a lot of now with a small startup to find good stuff and to do things and to make missions happen as Carl presented it here in during his lifetime, yeah. So and there will be a lot of challenges in the future as well for you. So once again, do you have questions? Don't be shy. Put questions out, come up as long as Carl is here on stage.
Maybe one last question regarding simplicity, or like you spoke about these conventional systems, but they seem to be quite complex. And I wonder, I don't know, maybe this is a stupid question, but um, speaking about electric thrusters or stuff like this, I think they seem to be quite simple. So why would you use one over the other?
Simplicity is super important. Robustness, simplicity usually translates to robustness. The more complicated you are, the farther away you get from a Rube Goldberg device, if you know what those are. And so simplicity is important. So from the point of view of the plumber, the xenon feed systems are indeed simpler, but the electric propulsion systems with high voltage and their power processors are incredibly complex. Whereas a regulated plumbing system, liquid system is very simple in that it's all just pressure drop and valves opening and closing. And what makes them complicated is the chemistry of the propellants and making sure that you control all sorts of variables. But very, very strongly agree with you that if you can get a simple system, self-pressurizing, you don't need a pressurization system, just a few valves, oh man, go with that. That's what you want to do. Usually it's like I said, the Opel and the Ferrari. If you can afford lower performance, you go with the high robustness, simple system. If you really need huge delta V and high performance, then you have to pay the price of more complexity and more risk and less robustness.
Okay, thank you.
Thank you for asking questions. You're the only one brave enough.
Yeah, I think this was a nice statement you just made regarding simplicity. Yeah. I started with a biprop system, and at the end of the satellite system I just built, I figured out what big advantage the monoprop system has. Huh? But when you just look to the ISP, you are more in favor of biprops. Huh? But ISP is not everything. No?
Order of magnitude difference in price.
Right, right.
We have the acronym here, KISS. Keep it simple, stupid.
Yeah,
That's my philosophy and my hairstyle.
yeah. Then you do not need a phone, no?
Genau.
Okay, thank you very much. If there's any last moment to raise questions or to participate to the discussion. If not, I would like to say thank you very much, Carl, for your time, for your preparation, and for all the explanations about these very interesting missions related to propulsion, and shows, yeah, propulsion is one of the most interesting thing, because you are then involved in nearly all space missions, because without propulsion, no mission is working. Huh?
Well done, well said. And thank you very much for giving me the opportunity to talk about myself and propulsion, my two favorite subjects. So
thank you very much.
I hope to meet you all someday.
Yes, for sure. When I will be in Washington, I will contact you. Huh?
Please do.
Okay. Thank you.
Thank you very much.
My pleasure.
Bye.